A satellite was watching the ocean. It saw something that made scientists go completely silent. A giant wave was moving across the Pacific, but it wasn't behaving like any wave they'd ever seen before. The patterns on their screens defied every prediction model, every assumption they'd built their careers on. Stay with me for the next several minutes, because what I'm about to share with you changes everything we thought we knew about tsunamis, and it might just be the key to saving thousands of lives in the future. What did this satellite actually capture? Why did it leave seasoned researchers speechless? And what does this mean for anyone living near a coastline? This isn't just another ocean story. This is about a moment when technology revealed something invisible to the human eye, something that's been happening beneath the surface every single time a tsunami strikes. But we've never had the tools to see it until now. The implications reach further than you might imagine. Before we go deeper, I want to ask you something. Hit that like button if you're curious about how science helps us understand nature's most powerful forces. Subscribe to this channel because we're going to explore discoveries that reshape our understanding of the planet. And drop a comment telling me where you're watching from, especially if you live near an ocean or have memories of tsunami warnings in your area. Your location matters more than you think when we're talking about waves that can cross entire oceans in hours, touching coastlines thousands of miles apart. Now, let me take you back to that moment. Picture a satellite orbiting high above Earth, its sensors pointed downward at the vast blue expanse of the Pacific Ocean. This wasn't just any satellite taking pretty pictures for geography textbooks. This was advanced technology designed specifically to measure water in ways we've never been able to measure it before. Every ripple, every shift in height, every movement of the ocean surface captured in extraordinary detail. When the earthquake struck off the coast of Russia's Kamchatka peninsula, that satellite happened to be in exactly the right position at exactly the right time. Scientists often talk about lucky breaks in research, those moments when preparation meets opportunity. This was one of those moments. The ground beneath the ocean floor shifted suddenly. Water displaced upward in massive volumes. A tsunami was born, radiating outward like ripples from a stone dropped in still water. Except these weren't ordinary ripples, and this wasn't still water. Within hours, data began streaming back to research centers. Scientists gathered around monitors, pulling up the satellite imagery, expecting to see what they'd always seen, what their computer models had predicted for decades. They expected to see a coherent wavefront, organized and predictable, moving in a pattern they could calculate and track. But that's not what appeared on their screens. The lead researchers leaned closer. Someone asked a question. Someone else checked the equipment, wondering if there was a malfunction. Because what they were looking at didn't make sense. The tsunami had fractured. It had scattered into multiple wave systems, each moving at different speeds, each taking slightly different paths across the ocean. The colors on the screen, representing wave heights and energy, formed a chaotic mosaic where there should have been clean, predictable lines. One scientist later described the feeling as watching something you thought was solid suddenly behave like liquid. Another said it was like discovering that a fundamental rule you'd memorized wasn't actually a rule at all, just an approximation that worked until you could finally see clearly enough to notice it didn't. This wasn't a small deviation. This wasn't a minor correction to existing theories. This was evidence that tsunamis, in their actual behavior as they cross real oceans with real topography and real complexity, do something fundamentally different from what we'd been assuming. And if our assumptions were wrong, then our prediction models were incomplete. And if our prediction models were incomplete, then our warning systems, the ones designed to tell coastal communities when to evacuate and when it's safe to stay, those systems were working with flawed information. You might be wondering why this matters so much. After all, we've had tsunami warnings for years. We've successfully evacuated people. We've saved lives. That's all true. But imagine trying to navigate using a map that's mostly correct but missing crucial details. You'll get close to where you need to go, but those missing details could mean the difference between arriving safely and getting off course. That's what we've been doing with tsunami predictions. Getting close, but not seeing the full picture. What this satellite revealed wasn't just academically interesting. It was practically critical. It opened questions that researchers immediately knew they needed to answer. How often does this scattering happen? Under what conditions? Can we predict which tsunamis will fragment and which will hold together? Can we use this information to give more accurate warnings about wave heights, arrival times, and impact zones? The answers to those questions were hidden in the data now flowing from space, waiting to be decoded, waiting to reshape how we protect ourselves from one of nature's most powerful forces. And the journey to understanding began with that single image, that moment of collective silence when scientists realized they were seeing something entirely new. Let's step back for a moment and talk about what tsunamis actually are, because understanding what happened requires understanding what we expected in the first place. You've probably heard about tsunamis in news coverage over the years. Images of water surging inland, affecting coastal towns, the aftermath that requires communities to rebuild. These events remain in our collective memory because of their scale, sudden onset, and the force they carry. But what causes a tsunami? At its most basic level, a tsunami is a series of waves created when something displaces a large volume of water very quickly. Usually that something is an underwater earthquake. The ocean floor shifts, sometimes lifting several feet in a matter of seconds across an area that might span hundreds of miles. All that water above the shifting ground has to go somewhere. It moves upward first, then spreads outward in all directions. Think of it like this. If you're sitting in a bathtub and you suddenly lift your knees up quickly, water rushes away from that spot, creating waves that travel to the edges of the tub. A tsunami works on the same principle, just at a scale that's almost impossible to comprehend. Instead of a bathtub, you're talking about entire ocean basins. Instead of your knees, you're talking about sections of the Earth's crust the size of cities moving vertically. Now here's what scientists thought they understood about how these waves behave once they're created. In the deep ocean, tsunami waves move incredibly fast, sometimes over 500 miles per hour, faster than a commercial jet. But they're also very long, stretched out over dozens or even hundreds of miles from crest to crest. If you were on a ship in the deep ocean when a tsunami passed underneath you, you probably wouldn't even notice it. The wave might only be a couple of feet high out there, spread out over such a long distance that it just feels like a gentle rise and fall. The danger comes when that wave approaches shallow water near coastlines. As the front of the wave enters shallower depths, it slows down, but the back of the wave, still in deeper water, keeps moving at the original speed. The wave compresses, like an accordion being pushed together. All that energy that was spread out over 100 miles gets squeezed into a much shorter distance. The wave grows taller, sometimes dramatically so. By the time it reaches shore, what was a barely noticeable swell in deep water can become a wall of water several stories high. This is the basic physics that every oceanography student learns. It's been tested and confirmed through countless observations. After major tsunamis in recent decades, the ones you might remember hearing about, scientists studied the data carefully. They measured wave heights at different locations. They timed when waves arrived at various coastlines. They built computer models that could simulate how a tsunami would travel across an ocean basin based on the earthquake's location, magnitude, and characteristics. These models became quite sophisticated. They could account for the general shape of the ocean floor. They could predict approximate arrival times for tsunamis reaching distant shores. They became the foundation of warning systems that span the entire Pacific Ocean and beyond. When an earthquake strikes in a location that could generate a tsunami, these systems spring into action. They estimate where the waves will go, how high they might be, and when they'll arrive. Then they send out warnings so people in threatened areas can evacuate to higher ground. And for the most part, these systems have worked. They've saved lives. Communities that received warnings had time to move inland, to climb to higher elevations to get out of harm's way. That's worth celebrating. But here's the thing about scientific understanding. It evolves. What we think we know completely often turns out to be what we know approximately. The difference between those two things might seem small, but improving from approximation to precision is how we make coastal communities safer. Scientists working with tsunami models knew their simulations were simplified versions of reality. They had to be. The ocean floor is incredibly complex. There are underwater mountain ranges, deep trenches, volcanic formations, ridges and valleys. Mapping all of that in perfect detail and then accounting for how every single feature might affect a passing tsunami wave would require computing power that's still beyond what we have. So they simplified. They smoothed out the ocean floor in their models. They assumed that waves would travel in relatively predictable, coherent patterns. This approach worked well enough for making general predictions. If a major earthquake happened off the coast of Japan, the models could tell you that a tsunami would reach Hawaii in roughly this many hours, and California a few hours after that. They could give you ballpark estimates of wave heights. That information was valuable. It gave people time to prepare. But there were always discrepancies. Sometimes waves arrived a bit earlier or later than predicted. Sometimes they were taller or shorter than the model suggested. Sometimes coastal areas that were expected to see significant impact experienced relatively minor effects, while other nearby areas that weren't considered high risk got hit harder. Scientists chalked these variations up to local factors, unique coastal geometries, measurement uncertainties. They were anomalies, not patterns, or so everyone thought. The Kamchatka Peninsula, where our story takes place, is a remote finger of land extending southward from Russia's far eastern coast. It's a wild place, sparsely populated, dominated by volcanic peaks and rugged terrain. The ocean surrounding it is deep and cold, part of the vast Pacific that stretches away in every direction. It's also a seismically active region. The Pacific Plate is diving beneath the North American Plate in this area, creating the conditions for powerful earthquakes. When earthquakes happen in remote locations like this, they don't always make international headlines unless they're extraordinarily large or unless they generate tsunamis that threaten populated areas. Even when tsunamis do occur, if they head out into the open Pacific away from major population centres, they might be noted by scientists but largely ignored by the general public. These are the events that become data points, entries in research databases, opportunities to test and refine models. Summer of 2025 was unremarkable in most ways. People around the Pacific were going about their lives. Researchers were analysing data from previous events, writing papers, attending conferences. Warning system operators were monitoring seismic activity as they always do, ready to respond if needed. And high above the Earth, a satellite called SWOT continued its orbital path, systematically scanning the ocean surface with unprecedented precision. SWOT stands for Surface Water and Ocean Topography. It's a joint mission between space agencies in the United States and France, launched with the goal of measuring water levels across the entire planet with remarkable accuracy. While earlier satellites could measure ocean heights, SWOT took this capability to a new level. It could detect changes as small as a few inches across wide swaths of ocean. It could create detailed maps showing the subtle rises and falls in the sea surface that indicate currents, eddies, and other oceanographic features. The satellite wasn't specifically designed to catch tsunamis. Its mission was broader, aimed at understanding ocean circulation, tracking freshwater resources, monitoring lakes and rivers. But tsunamis are, after all, changes in ocean surface height. If SWOT happened to be overhead when one occurred, its instruments would capture it in extraordinary detail. That's exactly what happened. The earthquake struck. The ocean floor shifted. Water surged upward and began its journey across the Pacific, and SWOT in its precise orbital dance came over the horizon at just the right moment to watch it unfold. The satellite's radar instruments swept across the affected area, bouncing signals off the ocean surface, measuring the distance with extreme precision, building a picture of what was happening below. Back on Earth, scientists didn't immediately realize what they had. The data took time to process. Raw satellite measurements need to be cleaned, corrected, analyzed. It's not like watching a video feed. It's more like receiving millions of individual measurements that need to be assembled into a coherent picture. Teams began working through the data as they normally would, expecting to see the usual patterns, perhaps gathering material for a research paper or adding another validation point to their tsunami models. Instead, they found something that would occupy their attention for months to come and would eventually lead to publications that made colleagues around the world take notice. They found evidence that the story of tsunami behavior was more complicated, more nuanced, and more challenging than anyone had fully appreciated. And that evidence was about to change the conversation about how we predict, track, and warn about these significant natural events, setting the stage for what came next in our understanding of the ocean's most powerful waves. The earthquake came without warning, as they always do. Deep beneath the ocean floor off Kamchatka's eastern coast, tectonic forces that had been building for years suddenly released. Rock fractured. Entire sections of the seafloor jolted upward. The shaking lasted less than a minute. But in that brief window, enough energy was released to power a large city for weeks. This wasn't just any earthquake. The magnitude was significant, the kind that gets attention from seismologists around the world. Within minutes, monitoring stations detected the seismic waves. Computer systems automatically calculated the earthquake's location, depth, and strength. Analysts quickly reviewed the data. The depth was shallow enough, and the magnitude large enough that tsunami generation was likely. The earthquake had occurred beneath the ocean, which meant water displacement was almost certain. Warning protocols activated. This is where the global tsunami warning system proves its value. Around the Pacific Basin, messages began flowing to emergency management agencies. Coastal communities in the potential impact zones received alerts. People living near shorelines heard sirens or received messages on their phones, telling them to move to higher ground as a precaution. For many, this was a familiar drill. The Pacific Ring of Fire produces enough significant earthquakes that tsunami warnings, while always taken seriously, are not uncommon. In this case, the models predicted that the tsunami would radiate outward from the Kamchatka region. Some wave energy would travel toward the Aleutian Islands and Alaska. Some would head south toward Japan. Some would move east into the broader Pacific. The initial calculations suggested moderate wave heights, concerning but not catastrophic for distant locations. Nearby coasts would need to be most cautious. Those farther away would see smaller effects. What no one on the ground realized was that they had an observer unlike any they'd had before. SWOT had launched a couple of years earlier and had been quietly revolutionizing how scientists study Earth's water systems. Its orbital path takes it over different parts of the planet with each pass, creating a gradually building global map of water surfaces. Every few days it covers the same regions again, tracking changes over time. On this particular day in summer, SWOT's orbit brought it over the North Pacific at a time that, purely by chance, aligned with the tsunami's generation and early propagation. The satellite wasn't hovering in one spot. It was moving at several miles per second, its instruments scanning a swath of ocean beneath its path. As it passed over the tsunami-affected region, those instruments were gathering data with extraordinary precision. The technology aboard SWOT is called radar interferometry. Without getting too deep into the technical details, here's what matters. The satellite sends radar pulses down to the ocean surface and measures how long they take to bounce back. By doing this across a wide area and combining information from multiple radar beams, it can determine the height of the ocean surface at thousands of points simultaneously. The precision is remarkable, able to detect height differences of just a few inches. For oceanographers, this capability opened new windows into understanding currents, eddies, and circulation patterns that were previously invisible or could only be inferred indirectly. For tsunami researchers, it represented an unprecedented tool, though one they hadn't specifically planned for. Tsunamis are rare enough and satellite passes are brief enough that catching one in the act requires luck. This time, luck was on the side of science. As SWOT's radar swept across the ocean, it was essentially taking a snapshot of the tsunami in its early stages. The wave system was still relatively close to its source, moving outward through deep water. This was the phase where the waves were traveling fastest, where their behavior was most influenced by the initial conditions of the earthquake and the immediate characteristics of the ocean basin they were crossing. The data streamed down to ground stations, routed to data centers, queued for processing. Scientists working with SWOT data have a constant flow of information to analyze. On any given day, they might be looking at rivers in South America, lakes in Africa, ocean currents in the Atlantic. When the Kamchatka earthquake occurred, some team members flagged the event, noting that SWOT might have captured relevant data. They began prioritizing the processing of that particular dataset, curious to see what it would show. Understand that these researchers weren't expecting a breakthrough, they were expecting confirmation. When you've studied a phenomenon for decades using certain tools and then you get a new, better tool, you generally expect to see the same patterns but with greater clarity. It's like upgrading from a grainy photograph to a high-resolution image. You expect to see more detail, but you don't expect the subject of the photo to look fundamentally different. As the data processed and the images began to form, researchers gathered to review them. This is standard practice. When you have information about a significant natural event, you want to look at it carefully, see what it tells you, consider whether it confirms or challenges your understanding. The team pulled up the visualizations showing ocean surface heights in the tsunami-affected area. The first thing they noticed was that the data quality was excellent. The satellite had captured the tsunami clearly. Wave heights stood out prominently above the background noise. You could see the structure of the wave system, how it was distributed across the ocean surface. This alone was exciting. Previous satellites had detected tsunamis, but never with this level of detail and coverage. Then they started looking more closely at that structure. This is where the confusion began. One researcher pointed at the screen, asking a colleague to confirm what they were seeing. Someone suggested checking the data processing algorithms to make sure nothing had gone wrong, in translating raw measurements into visualized results, because the pattern on the screen didn't match the pattern they expected. Instead of seeing a relatively uniform wavefront moving outward from the earthquake source, they saw something much more complex. The tsunami had split into multiple components. There were areas of high wave energy separated by areas of lower energy. The wave system looked almost fragmented, like it had shattered into pieces that were each going their own way. Imagine expecting to see a single ripple expanding in a circle, and instead seeing that ripple break into several smaller ripples, each propagating at slightly different speeds and angles. That's what they were looking at. The tsunami wasn't behaving as a coherent, unified wave. It was behaving as a collection of related but distinct wave groups. The scientists spent hours that day examining the data from every angle. They looked at different ways of visualizing it. They checked their understanding of the satellite's measurements. They reviewed what they knew about the earthquake itself, confirming that it was a straightforward seismic event, nothing unusual that might explain strange tsunami behavior. Everything checked out. The data was good, the earthquake was normal, but the tsunami's behavior was anything but. One team member suggested comparing the satellite observations to what their computer models predicted for this event. They ran simulations using the earthquake parameters, the known ocean floor topography in the region, and the standard tsunami propagation models. The simulations produced results that looked like what they'd always seen: clean wave fronts, predictable patterns, organized propagation. Then they overlaid the simulation results with the satellite observations. The mismatch was obvious. The model showed the tsunami as a coherent system. The satellite showed it as fragmented and complex. The model predicted wave heights and patterns that didn't align with what was actually measured. It wasn't that the model was completely wrong. The general energy levels were in the right ballpark. The overall direction of propagation was correct. But the fine details, the actual structure of the wave system, those were way off. This was the moment when the significance started to sink in. For years, scientists had been using models that smoothed over complexity, assuming that the approximation was good enough. Now they were seeing, for the first time with this level of clarity, that the approximation missed important behavior. The tsunami was doing something that the models couldn't capture, something that had been happening all along but was invisible until the right technology came along to reveal it. There's a particular feeling that comes with this kind of discovery. It's not quite excitement, because the implications are serious and require careful thought. It's not quite confusion, because the data is clear even if the explanation isn't immediately obvious. It's more like a shift in perspective, a realization that you need to rethink things you thought were settled. For the SWAT team looking at that data, this was one of those moments. They began reaching out to colleagues, tsunami specialists, ocean dynamics experts, anyone who might help make sense of what they were seeing. Papers were pulled from archives. Previous tsunami events were revisited. People started asking questions. Had anyone else seen hints of this behavior before? Were there measurements from other tsunamis that showed similar patterns but had been dismissed as noise or attributed to local effects? Was this unique to this particular event, or was it a general phenomenon that had simply gone unnoticed? The conversations that followed would span months. Research groups began collaborating. Data was shared. Analyses were conducted and repeated. Hypotheses were proposed and tested. Slowly, a picture began to emerge of what was actually happening when tsunamis cross the ocean, and why that matters for how we predict and prepare for them. But in that initial moment, sitting in front of screens showing patterns that defied expectations, the researchers knew they'd stumbled onto something important, something that would reshape their field, and as we'll explore next, something that would ultimately make coastal communities safer by revealing the truth about how these waves really behave in the complex, messy reality of Earth's oceans. Let me describe what appeared on those screens in a way that makes the strangeness clear. The visualization systems used for satellite ocean data typically show water heights using color coding. Blues and greens represent normal sea level or slight variations. Yellows, oranges, and reds represent higher elevations, places where the water surface is raised above the baseline. When you're looking at a tsunami, those warm colors show you where the wave energy is concentrated. What the scientists expected to see was a pattern like concentric circles radiating from a central point, similar to dropping a stone in water. The colors would be brightest near the source, gradually fading as the waves spread outward and their energy dispersed. There might be some irregularities based on ocean floor features directly beneath the source, but the overall pattern should be relatively smooth and organized. What they actually saw looked more like someone had taken that organized pattern and scrambled it. Instead of concentric circles, there were patches of orange and red scattered across the image in ways that seemed almost random. One patch would be here, another over there, separated by areas of yellow or green indicating lower wave heights. The tsunami hadn't maintained its coherent structure. It had fractured. Following the individual patches with their eyes, researchers could see that these fragments of wave energy were moving in slightly different directions. Some were tracking northeast, others were heading more eastward. Their speeds, calculated from the spreading pattern, also varied. The tsunami had become a family of related waves rather than a single unified system. This wasn't a subtle effect. It wasn't something you needed specialized training to notice. Anyone looking at the image could see that the pattern was complex and broken up. The question was why? What could cause a tsunami to behave this way? And more importantly, had this been happening with every tsunami, hidden from view until now? One of the senior researchers on the team later described their reaction as a mix of fascination and concern. Fascination because they were seeing something genuinely new, something that revealed gaps in the existing understanding. Concern because those gaps had real-world implications. If tsunamis don't actually travel in the neat, predictable ways the models suggested, then the warnings based on those models might be giving people inaccurate information about when waves would arrive and how high they'd be. Think about what that means practically. Imagine you're an emergency manager in a coastal town. You receive a tsunami warning that says waves will arrive in 6 hours with an estimated height of several feet. You make decisions based on that information. You order evacuations of low-lying areas. You position emergency responders. You inform the public. Now imagine that the actual tsunami arrives an hour earlier or later than predicted, or comes in with a completely different wave pattern than expected, or hits certain parts of your coastline much harder than others in ways the warning didn't anticipate. Those discrepancies could affect evacuation outcomes and community safety. This wasn't theoretical. Researchers went back and looked at records from past tsunami events. They found cases where wave arrival times were off by significant margins, cases where damage patterns along coastlines didn't match what models predicted, cases where emergency responders had been caught off guard by unexpected wave behavior. At the time, these incidents were attributed to various local factors, the unpredictability of nature, the limitations of the data available. But now, looking at them through the lens of what SWOT had revealed, a different explanation emerged. Maybe the tsunamis themselves were behaving in ways the models simply couldn't capture. The researchers began drafting a paper documenting what they'd observed. In science, observations alone aren't enough. You need to explain them. You need to propose a mechanism, a reason why things behave the way they do. The team started developing hypotheses about what could cause tsunami fragmentation. This is where expertise in ocean dynamics became crucial. Tsunamis travel through water, and water is never uniform. The ocean floor has topography every bit as complex as the landscape above sea level. There are underwater mountain ranges that rival the Himalayas. There are trenches deeper than Mount Everest is tall. There are volcanic seamounts rising thousands of feet from the surrounding floor. There are ridges, plateaus, canyons, and valleys. All of this affects how water moves. When a tsunami wave encounters a change in depth, it responds. If the water gets shallower, the wave slows down and grows taller. If the water gets deeper, the wave speeds up and spreads out. These effects are well known and are included in tsunami models, at least in a general way. But the models typically use simplified representations of the ocean floor, smoothing out smaller features, averaging depths over large areas. It's computationally necessary because simulating every detail would require impossible amounts of computing power. What the researchers realized was that those smoothed-over details matter more than anyone thought. A tsunami traveling across the Pacific doesn't encounter a smooth gradient from deep to shallow. It encounters a chaotic landscape of depth variations. Every seamount it passes over, every ridge it crosses, every trench it spans affects the wave differently. Some parts of the wave speed up while others slow down. Some parts bend toward shallower water while others bend toward deeper channels. The wave starts to lose its coherence. There's another factor too. Tsunamis aren't actually single waves. They're wave trains, a series of waves following one after another. Each wave in the train responds to the ocean floor features it encounters. Over time, as the waves interact with the complex topography and with each other, the system becomes increasingly disorganized. What started as a relatively organized series becomes a scattered collection of wave groups. Think of it like this. Imagine a line of runners starting a race on a flat track. They begin together, moving at similar speeds. Now imagine that track starts having hills, valleys, rough patches, and smooth sections randomly distributed across it. Some runners hit a hill and slow down, others find a smooth patch and speed up. Soon, the neat line of runners has broken into clusters spread across the course. That's essentially what happens to tsunamis crossing the real complex ocean floor. Previous tsunami observations had hints of this behavior, but without the comprehensive view SWOT provided, those hints were hard to interpret. Coastal wave gauges might record a complex series of waves arriving at different times and heights, but from a single point measurement, it's hard to say whether that complexity existed out in the ocean or developed as the waves interacted with the local coastal geometry. SWOT gave researchers the ability to see the wave system's structure while it was still in the open ocean, far from shore, revealing that the complexity was intrinsic to how the waves were traveling. The paper went through multiple drafts. Colleagues were brought in to review it. The satellite data was checked and rechecked. The team wanted to be absolutely certain they weren't making claims that couldn't be supported. They ran additional analyses, looking at the data from different angles, testing alternative explanations. Everything kept pointing to the same conclusion. The tsunami had fragmented in ways the models couldn't predict, and this fragmentation was likely a common feature of tsunami propagation that had simply been invisible until now. When the paper was finally ready, it was submitted to a peer-reviewed journal. Other scientists reviewed it anonymously, checking the methodology, the data analysis, the conclusions. This is how science works. You don't just announce findings, you subject them to scrutiny. You invite experts to find flaws if they exist. In this case, the reviewers found the work solid. The observations were clear, the reasoning was sound, the implications were significant. The paper was accepted for publication. It appeared in print in early the following year, accompanied by the striking images from SWOT showing the fragmented tsunami structure. The title was technical, as scientific papers tend to be, but the content was revolutionary for the field. It presented direct observational evidence that tsunami behavior in the open ocean was more complex than existing models accounted for. Within the tsunami research community, the paper generated immediate interest. Other groups began looking at their own data in new ways. Previous events were reanalyzed. Computer modelers started working on ways to incorporate finer-scale ocean floor details into their simulations. There was recognition that this wasn't just an academic curiosity. This was information that needed to make its way into operational warning systems. But scientific papers, no matter how important, don't instantly change how things work in the real world. Warning systems are complex infrastructures involving multiple agencies, established protocols, and carefully validated procedures. Updating them requires careful work. New models need to be developed, tested, and validated before they can replace existing ones. Data about ocean floor topography needs to be incorporated at higher resolution. Computing systems need to be upgraded to handle the increased complexity. All of that takes time. It requires funding, coordination, and sustained effort. The researchers who discovered the tsunami fragmentation became advocates for these improvements. They gave presentations at conferences. They met with officials from warning system agencies. They made the case that understanding this phenomenon better could lead to more accurate predictions, better warnings, and ultimately saved lives. There was also the question of what other tsunamis might reveal if observed with similar technology. SWOT continues to orbit, and while the chance of catching another major tsunami is relatively small simply because they're rare events, the satellite's data is valuable for many other purposes. Meanwhile, researchers began looking forward to future satellite missions that might be designed with tsunami observation more specifically in mind. The story of this discovery is a reminder of how scientific progress often works. Sometimes breakthroughs come from asking entirely new questions. Other times they come from developing new tools that let you see things you couldn't see before. In this case, SWOT wasn't built to revolutionize tsunami science specifically, but it happened to have the right capabilities at the right time to reveal something that had been hidden in plain sight all along. For the scientists involved, there was satisfaction in uncovering something genuinely new, but also a sense of responsibility. This wasn't just interesting data. This was information that related to public safety. The fragmented behavior of tsunamis meant that predictions could be improved But it also meant that current predictions had limitations that needed to be acknowledged and addressed. The path forward required not just more research, but also communication with the people who use tsunami warnings to make life and death decisions. And as we'll explore next, understanding exactly why this fragmentation happens comes down to the hidden landscape beneath the waves and how it shapes every movement of the ocean above it. Now comes the fascinating part, the explanation. Why do tsunamis fragment? What's actually happening beneath the surface that causes these waves to scatter and break into separate components? The answer lies in a combination of physics, geography, and the sheer complexity of the ocean environment. Let me walk you through it in a way that makes intuitive sense without needing an advanced degree. Start with the basic fact that waves travel at different speeds depending on water depth. This is true for all water waves, not just tsunamis. In deeper water, waves move faster. In shallower water, they slow down. The relationship is straightforward. The speed of a tsunami wave is roughly equal to the square root of the water depth multiplied by gravity. That means if you double the depth, the wave speed increases by about 40%. Why does this matter? Because the ocean floor is anything but uniform. Picture the Pacific Ocean floor. It's not a smooth bowl shape gradually deepening toward the center. It's a wild landscape. There are mid-ocean ridges where tectonic plates are spreading apart, creating underwater mountain ranges. There are subduction zones where plates dive beneath each other, forming deep trenches. There are thousands of volcanic seamounts, some rising nearly to the surface, others standing as isolated peaks on the deep ocean floor. There are plateaus, escarpments, channels, and fracture zones. When a tsunami encounters this complex topography, different parts of the wave travel over different depths. A section of the wave passing over a seamount is in shallower water and slows down. A section passing through a deeper channel maintains a higher speed. This creates what's called wave refraction. The wavefront, which might have started out relatively straight, begins to bend and curve as parts of it travel at different speeds. Think about a line of people holding hands and walking forward together. As long as they're all walking at the same speed on flat ground, the line stays straight. But now imagine some people encounter mud that slows them down, while others are still on firm ground. The line starts to curve and stretch. Eventually, if the speed differences are large enough and last long enough, the line might break apart. That's essentially what happens to tsunamis crossing variable ocean floor topography. But it's not just about simple refraction. There's another phenomenon at play called wave dispersion. Remember that tsunamis are actually a series of waves, not a single wave. These waves have different wavelengths and periods. Some are longer, stretched out over greater distances, others are shorter. In deep water, all these waves travel at about the same speed, so they stay grouped together. But as they encounter topographic features, the longer waves and shorter waves start to respond differently. Longer wavelength waves feel the ocean floor over a broader area. They kind of smooth out the effects of smaller topographic features. Shorter wavelength waves are more sensitive to local depth changes. They respond more dramatically to seamounts, ridges, and other structures. Over time, this causes the wave train to spread out. The different components start separating. What began as a coherent packet of wave energy becomes dispersed across a wider area and time span. There's also wave interference to consider. As the tsunami spreads out and different parts travel different paths at different speeds, they start to interact with each other. Waves coming from slightly different directions can meet and either reinforce each other or cancel each other out. When two wave crests meet, they combine to create a higher peak. When a crest meets a trough, they can partially or completely cancel out. This constructive and destructive interference adds another layer of complexity to the wave pattern. Imagine throwing several stones into a pond at slightly different times and locations. Each stone creates its own set of ripples. As those ripples spread out, they overlap and create complex patterns where some areas have high waves and other areas have relatively calm water. The ocean is like that pond, except the topography is creating the equivalent of stones being thrown in different patterns, and the tsunami wave train is interacting with itself across hundreds of miles. Now, let's talk about what all this meant for the traditional tsunami models. Those models were built on simplifications. They had to be. You can't simulate every single feature of the ocean floor at a resolution of a few feet across an entire ocean basin. The computing power required would be astronomical. So modelers made reasonable approximations. They smoothed the topography, representing it at a resolution of maybe a few miles or even tens of miles. They assumed that the overall shape was what mattered, not the small-scale details. For many purposes, those approximations worked reasonably well. If you wanted to know whether a tsunami would reach Hawaii in 6 hours or 8 hours, the simplified models could give you a useful answer. If you wanted to know whether wave heights would be in the range of a few feet or tens of feet, the models could provide guidance. But when it came to predicting the detailed structure of the wave system, exactly when the peaks would arrive, how the energy would be distributed along a coastline, the models struggled. The SWOT observations made this clear. The satellite could see structure in the tsunami at scales of a few miles or even less. At those scales, the effects of seamounts, ridges, and other topographic features became visible in the wave pattern. The tsunami wasn't acting like a smooth, uniform wavefront. It was acting like a complex system responding to every bump and valley it encountered. Scientists began to appreciate that the ocean floor details they'd been smoothing over were actually critical to understanding real tsunami behavior. A seamount that rises a couple of miles above the surrounding floor might seem insignificant when you're modeling an ocean that's several miles deep on average. But to a tsunami wave passing over it, that seamount creates a significant depth change. The wave slows down, bends around the obstacle, and might even partially reflect off it. Multiply this effect across hundreds or thousands of such features, and you get the complex, fragmented wave pattern SWOT observed. Let me give you a comparison that might help. Imagine trying to predict how water flows down a mountainside. If you model the mountain as a smooth cone, you might predict that water flows straight down in evenly distributed streams. But real mountains have rocks, gullies, ridges, and valleys. Water doesn't flow smoothly down. It channels into streams, splits around obstacles, pools in depressions, and creates complex patterns. You can't predict those patterns by modeling a smooth cone. You need to account for the actual detailed topography. The same principle applies to tsunamis in the ocean. The simplified, smooth representation of the ocean floor can give you general trends, but it misses the detailed behavior caused by the real complex landscape beneath the waves. And that detailed behavior matters, especially when you're trying to predict what will happen when the tsunami reaches populated coastlines. Researchers also realize that some tsunamis would fragment more than others. The degree of fragmentation depends on several factors. How far does the tsunami travel? Longer journeys across the ocean mean more opportunities to encounter topographic features and more time for dispersion to spread the wave train out. What's the character of the ocean floor along the path? Some routes cross relatively smooth abyssal plains, others cross highly variable terrain. How energetic is the tsunami to begin with? Larger, more powerful tsunamis might maintain coherence better than smaller ones. This explains some of the historical inconsistencies. Some past tsunamis had arrived at distant shores in relatively coherent pulses, roughly matching model predictions. Others had arrived as complex series of waves spread over hours, confusing forecasters. The difference wasn't random. It was related to the paths those tsunamis took and the topography they encountered. But without observations like what SWOT provided, connecting those dots was difficult. Now, understanding the mechanism behind tsunami fragmentation opened up new possibilities. If you know why something happens, you can start to predict when and how it will happen. This meant that with better ocean floor maps and more sophisticated models, scientists could potentially forecast not just the general arrival of a tsunami, but also its detailed structure. They could say not just that waves will arrive in 6 hours, but that there will likely be a leading wave followed by several more over the next few hours, with particular spacing and heights. Getting to that level of prediction requires work. Ocean floor mapping efforts have been ongoing for decades, but large areas of the ocean are still not mapped at high resolution. Satellite measurements, ship-based sonar, autonomous underwater vehicles, all these tools contribute to building better maps. Every improvement in the maps means better ability to model how tsunamis will interact with the topography. It also requires more sophisticated computer models. Instead of running simulations on a smoothed ocean floor, modelers need to incorporate the detailed topography. This dramatically increases the computational load. A simulation that might have taken hours on simplified topography could take days or weeks with full detail. But computing power keeps improving, and techniques for efficient simulation are constantly being developed. What seemed impractical a few years ago becomes feasible. There's also the question of real-time application. When an earthquake strikes and a tsunami warning needs to go out quickly, there might not be time to run highly detailed simulations. Warning systems need to provide information within minutes, not hours or days. So researchers are working on hybrid approaches. Perhaps you run a quick simulation on simplified topography to get initial estimates, then refine those estimates with more detailed models as time allows. Perhaps you pre-compute a library of scenarios for different earthquake locations and magnitudes, using detailed topography so that when a real event occurs you can quickly look up the closest pre-computed case. These are the kinds of practical challenges that come with moving from scientific discovery to operational implementation. The discovery itself, the observation that tsunamis fragment in complex ways due to ocean floor topography, is now established. The question is how to use that knowledge to improve the systems that protect people. It's a question being actively worked on by researchers and warning system operators around the world. What's clear is that the old approach, while valuable and certainly better than having no warnings at all, was incomplete. It gave approximations when what we really need is precision. Lives depend on getting the details right. Communities need to know not just that a tsunami is coming, but when the waves will arrive, how many pulses to expect, which areas of the coastline will be most affected, and how long the danger will last. The fragmentation phenomenon discovered through SWOT observations directly relates to all of those questions. In some ways, this discovery is humbling. It reminds us that nature is more complex than our models, that there's always more to learn, that assumptions we take for granted might be oversimplifications. But it's also empowering. We now know something we didn't know before. We've seen tsunami behavior at a level of detail that was previously hidden. We have a clearer picture of what's actually happening out there in the open ocean when these waves travel thousands of miles across the Pacific. And with that knowledge comes the opportunity to build better tools, create better warnings, and ultimately keep more people safe when the ground shakes and the ocean responds, which leads us naturally to the question of what all this means for the warning systems we depend on today and how they're evolving to incorporate these new insights. Let's bring this back to the practical reality. People living in coastal communities around the Pacific and other ocean basins rely on tsunami warning systems to tell them when they're in danger. These systems are the result of decades of work by scientists, engineers, and emergency management professionals. They represent genuine achievements in applying scientific knowledge to protect lives. But they're also built on models and assumptions, and as we've just learned, some of those assumptions were incomplete. When a major earthquake occurs in a location that could generate a tsunami, monitoring centers immediately go into action. Seismologists analyze the earthquake data. They determine its location, magnitude, depth, and faulting mechanism. All of this information feeds into models that estimate whether a tsunami was generated, and if so, how large it might be. Within minutes, initial assessments are made. Warnings are issued if appropriate. These initial warnings are necessarily broad. They might say that a tsunami is possible, that coastal areas should be on alert, that more information will follow. As time passes and more data comes in, the warnings are refined. Coastal tide gauges and ocean buoys detect the tsunami passing and provide measurements of actual wave heights. This real-world data helps update the forecasts. Warnings can be narrowed to specific regions, or cancelled for areas where the threat turns out to be minimal. This system has worked well in many cases. It's provided advance notice that saved countless lives, but it's not perfect. There have been instances where predicted arrival times were off by significant amounts, cases where expected wave heights didn't match reality, situations where the pattern of waves was more complex than forecasts suggested. These discrepancies are frustrating for emergency managers trying to make decisions and concerning for communities trying to know whether they're truly safe. The discovery of tsunami fragmentation helps explain many of these discrepancies. If the models are based on simplified ocean floor topography and assume relatively coherent wave propagation, but the actual tsunamis are fragmenting and creating complex wave patterns, then naturally there will be mismatches between predictions and reality. It's not that the people running the warning systems are doing anything wrong, it's that the underlying models, through no fault of the operators, don't fully capture the physics of what's happening. Now that we understand the fragmentation phenomenon better, we can work toward improving the models. This is already happening. Research groups around the world are developing next-generation tsunami simulation systems that incorporate higher-resolution ocean floor data. They're testing new algorithms that can better represent how waves interact with complex topography. They're running validation studies, comparing their improved models against past tsunami events to see if the new approaches do better at reproducing what actually happened. Early results are promising. When researchers model past tsunamis using detailed topography and accounting for wave dispersion, and interference effects, the simulations match observations better than the old simplified models did. The predicted wave arrival times are closer to what was actually measured. The predicted pattern of waves, how many pulses and with what spacing, matches recorded data more accurately. The distribution of wave energy along coastlines corresponds better to observed damage patterns. This validation work is crucial because you can't just implement a new model in an operational warning system without thoroughly testing it first. Lives depend on these systems working correctly. If a new model produces less accurate predictions than the old one, or if it's too slow to run in the time available, or if it has technical issues that haven't been discovered, implementing it could reduce effectiveness. So researchers test extensively, compare results, identify strengths and weaknesses, and gradually build confidence that the new approaches are genuinely better. There's also the practical matter of computing resources. Warning centers need to generate forecasts quickly. When an earthquake strikes, every minute counts. People need time to evacuate to higher ground. If running a detailed simulation takes too long, the forecast arrives too late to be useful. This creates a tension between accuracy and speed. More detailed models are more accurate but slower to run. Simpler models are faster but less accurate. Researchers are attacking this problem from multiple angles. One approach is to simply use more powerful computers. As computing technology advances, what was too slow a few years ago becomes feasible today. Warning centers are upgrading their systems, investing in high-performance computing clusters that can run complex simulations in reasonable timeframes. Another approach is to optimize the simulation algorithms themselves, finding ways to compute the same results more efficiently. And a third approach is to pre-compute many possible scenarios, creating a database that can be quickly searched when a real event occurs. Imagine having detailed simulations already done for earthquakes of various magnitudes at thousands of possible locations around the Pacific. When a real earthquake happens, you check which pre-computed scenario most closely matches the actual event, and you use that as your forecast. You could even blend several similar pre-computed scenarios to create a forecast tailored to the specific earthquake. This hybrid approach combines the speed of lookup with the accuracy of detailed modeling. All of these strategies are being explored and implemented in different combinations by warning centers around the world. The goal is the same. Use the new understanding of tsunami behavior to provide more accurate, more reliable warnings to coastal communities. Get the arrival times right. Predict the number and spacing of wave pulses. Identify which stretches of coastline will see the highest impacts. Give emergency managers the information they need to make optimal decisions about evacuations and resource deployment. There's also an important human element to consider. Tsunami warnings need to be trusted by the people receiving them. If warnings frequently overestimate the threat, people start to ignore them, a phenomenon sometimes called warning fatigue. If a community evacuates multiple times for tsunamis that turn out to be minimal, residents may decide not to evacuate the next time, even when the danger is real. Conversely, if warnings underestimate threats, people may not take them seriously enough, leading to inadequate preparations. Better models that more accurately reflect real tsunami behavior can help with this trust issue. If warnings are more accurate, if they correctly distinguish between situations that require immediate evacuation and situations where caution is warranted but evacuation isn't necessary, then people learn to trust the system. They see that when the warning says evacuate, it's genuinely important. When the warning says stay alert but you're not in immediate danger, that turns out to be true as well. This doesn't mean warnings will ever be perfect. There's inherent uncertainty in any forecast about a natural event. Every earthquake is unique. The ocean floor topography, while better mapped, is not known in every detail everywhere. Tsunamis can interact with coastal features in complex ways that are hard to predict. But there's a big difference between forecasts that are right most of the time, with known uncertainty ranges, and forecasts based on incomplete models that can miss important aspects of the phenomenon. The research community is also working on communicating uncertainty better. Instead of saying a tsunami will arrive at a specific time with a specific height, warnings are increasingly presenting ranges and probabilities. Wave arrival expected between this time and that time. Heights likely in this range with a small chance of exceeding it. This kind of probabilistic forecasting gives decision-makers a more complete picture. It acknowledges the limits of prediction while still providing actionable information. Another important direction is regional customization. Different parts of the Pacific Basin have different characteristics. The ocean floor topography varies. The coastlines have different shapes and vulnerabilities. Warning systems are being developed that can account for these regional differences, providing forecasts specifically tuned to local conditions rather than generic estimates. For instance, some coastlines are relatively straight with gradually deepening offshore waters. Others have bays, inlets, and complex geometries that can focus or amplify tsunami waves. Some areas have protective reefs or barrier islands offshore. Others are directly exposed to the open ocean. Models that incorporate these local details can predict more accurately how a tsunami will behave when it reaches a particular community. This localization effort requires collaboration between national warning centers and local authorities. The national centers provide the large-scale tsunami forecasts. Local agencies contribute detailed information about their specific coastlines, bathymetry, and vulnerabilities. Together, they create tailored warnings that are most useful for the actual geography and population at risk. Education is another piece of the puzzle. Even the best warning systems only help if people know how to respond. Communities in tsunami-prone regions conduct regular drills. Schools teach children what to do if they feel an earthquake near the coast or hear a tsunami siren. Signs mark evacuation routes and safe zones. This culture of preparedness, combined with accurate and timely warnings, creates layers of protection. The work being done to improve tsunami predictions based on the SWOT observations and the understanding of wave fragmentation feeds into all of this. It's not just an academic exercise. Every improvement in accuracy, every additional minute of advance warning, every better assessment of which areas are most at risk translates into better decisions and safer outcomes when a real tsunami occurs. Scientists involved in this work carry a sense of responsibility. They know their research has direct implications for public safety. They're not just trying to publish papers and advance their careers, they're trying to provide tools that will help protect communities. That motivation drives the urgency and care with which they approach the work of improving models and working with warning system operators to implement new capabilities. There's still much to be done. Ocean floor mapping continues, filling in gaps and increasing resolution. Computational methods keep improving, allowing more detailed simulations. Satellite technology advances, with future missions planned that will build on SWOT's capabilities. Each piece contributes to a gradually improving system for understanding and predicting tsunamis. And while we'll never eliminate all uncertainty, every step forward in understanding makes us better prepared for the reality that tsunamis will continue to occur as long as tectonic plates continue to shift and earthquakes continue to shake the ocean floor, which brings us to the larger context of how technology and human ingenuity work together to protect us from natural forces far beyond our control. Step back for a moment and consider the broader picture here. What we're really talking about is the relationship between humanity and the natural forces that shape our planet. Earthquakes, tsunamis, hurricanes, volcanic eruptions, these aren't new phenomena. They've been occurring for as long as Earth has existed. What's new is our ability to observe, understand, and prepare for them. The SWOT satellite represents a particular kind of achievement. It's a tool that extends our senses beyond what's naturally possible. We can't see the subtle rises and falls of the ocean surface that indicate currents or tsunamis. We can't be everywhere at once to observe how water moves across the planet. But we can build instruments that can do these things, launch them into orbit, and receive the data they collect. In doing so, we gain a perspective that would otherwise be completely inaccessible. This mission is also an example of international cooperation. SWOT was built jointly by space agencies in the United States and France, with contributions from other nations. It serves the entire world. The data it collects is made available to researchers and operational agencies globally. There's no territorial boundary to ocean science. Tsunamis cross international borders. The knowledge we gain benefits everyone. Think about how different our situation is today compared to just a few generations ago. 100 years ago, if a tsunami was generated by an earthquake, the only warning for distant coasts was the time it took for the waves to travel across the ocean. People might have a few hours or at most a day to notice unusual ocean behavior and react. Often, they had no warning at all. The waves simply arrived with devastating force. 50 years ago, we had basic seismic networks and some understanding of tsunamis, but forecasting ability was limited. Warnings were crude, often amounting to an earthquake occurred, so coastal areas should be cautious. Today we have detailed seismic monitoring worldwide, networks of ocean buoys that detect tsunamis, sophisticated computer models. and now satellite observations at unprecedented resolution. The improvement is dramatic, but technology alone isn't the complete answer. It provides information, but people make decisions. Communities need to invest in preparedness. Governments need to support warning infrastructure. Individuals need to know what to do when warnings are issued. The technology enables better outcomes, but only when it's embedded in systems that connect observations to action. SWOT is one satellite among many that watch over Earth. There are satellites monitoring weather patterns, tracking hurricanes, measuring atmospheric composition, observing ice sheets, detecting forest fires, and dozens of other tasks. Together, they form a kind of nervous system for the planet, constantly sensing what's happening and relaying that information to us. This flood of data presents challenges. How do we process it all? How do we extract meaningful information from millions of measurements every day? This is where advances in computing, data science, and artificial intelligence come in. Algorithms sift through satellite data, identifying patterns, flagging anomalies, generating alerts. Human experts then interpret these automated analyses, applying judgment and context that machines can't provide. The combination of automated processing and human expertise is powerful. Machines can watch for patterns across vast datasets that no human could monitor continuously. Humans can recognize when something unusual is happening that might require closer attention, or when automated systems are producing questionable results. Together, they form a hybrid intelligence that's more capable than either alone. Looking forward, the trajectory is toward even more capable observation systems. Future satellites will have better instruments, higher resolution, and faster data delivery. The James Webb Space Telescope taught us lessons about engineering complex instruments for space that will benefit Earth observation satellites. Commercial space companies are reducing launch costs, making it more affordable to put multiple satellites in orbit for redundant coverage. There are also plans for constellations of smaller satellites working together. Instead of one large satellite like SWAT that can only observe a particular location every few days as its orbit brings it overhead, imagine a network of satellites that can provide continuous or very frequent coverage. This would allow tracking of dynamic phenomena like tsunamis from generation through propagation to coastal arrival. It would reveal behaviors and patterns that single snapshot observations miss. Beyond satellites, other technologies contribute to ocean observation. Autonomous underwater vehicles cruise beneath the surface, gathering data on ocean currents, temperature, and chemistry. They can stay at sea for months, following programmed routes or responding to changing conditions. Drifting buoys float on the surface, measuring wave heights and ocean properties, transmitting their data via satellite uplinks. Moored buoys stationed at fixed locations provide continuous time series of conditions at key points. All this information flows into data centers where it's archived and made available to researchers and forecasters. The amount of data is staggering. Petabytes of measurements collected every year, all needing to be stored, indexed, and analyzed. This creates challenges and opportunities. Challenges because managing that much data requires substantial infrastructure and expertise. Opportunities because within those enormous data sets are insights waiting to be discovered. Scientists are finding connections between phenomena that weren't obvious before, how ocean temperatures affect hurricane intensification, how melting ice sheets influence ocean circulation patterns, how underwater topography channels currents that affect nutrient distribution and marine ecosystems. Each connection reveals something about how the Earth system works as an integrated whole rather than a collection of isolated components. In the context of tsunamis, these connections matter. Tsunami behavior is influenced not just by the earthquake that generates them and the ocean floor topography, but also by ocean currents, tides, and other factors. A tsunami arriving at a coastline during high tide can have greater impact than the same tsunami at low tide. Understanding these interactions allows for more nuanced predictions. There's also something humbling about all this technology and knowledge. Despite our satellites and sensors and models, nature still surprises us. The SWOT discovery is a perfect example. We thought we understood tsunami propagation reasonably well, but direct observation revealed complexity we'd missed. This pattern repeats across science. Every time we develop tools to see more clearly, we discover that reality is richer and more intricate than we imagined. This should give us a healthy respect for the natural world. It's powerful, complex, and operates on scales from the microscopic to the planetary. Our knowledge, while growing, is always incomplete. There's always more to learn. This doesn't mean we should give up on trying to understand and predict. It means we should remain humble and open to revising our understanding when new evidence appears. It also means we should value the process of science itself. Science isn't a fixed body of facts. It's a method for investigating reality, testing ideas against observations, and gradually building more accurate models of how things work. The tsunami fragmentation story illustrates this beautifully. Observation led to questions. Questions led to analysis. Analysis led to new understanding. New understanding is being incorporated into practical applications, and the cycle continues. The benefits of this process extend beyond tsunami warnings. The same satellite technologies, modeling approaches, and data analysis methods used for tsunami research apply to other areas. Climate science uses similar tools to track changing ocean currents and sea level. Weather forecasting relies on satellites and models. Resource management for fisheries depends on understanding ocean conditions. The investment in Earth observation infrastructure pays dividends across multiple domains. As we look to the future, the trend is clear. More sensors, better models, faster communications, and wider availability of information. This trajectory suggests that our ability to understand and respond to natural hazards will continue improving. We'll never eliminate risk completely. Earthquakes will still happen, tsunamis will still be generated, but our capacity to anticipate, warn, and protect will keep getting better. This is reason for optimism, not complacency. Progress requires sustained effort and investment. It requires collaboration across nations, disciplines, and sectors. It requires training the next generation of scientists and engineers who will develop even better tools. It requires policymakers who understand the value of research and operational systems. And it requires public awareness and support for the infrastructure that keeps communities safe, which naturally leads us to consider the human side of this story, and the communities whose lives and safety are directly connected to how well we understand the waves that occasionally cross thousands of miles of ocean to reach their shores. Let me bring this down to the human level, to the scale where all this science and technology actually matters most. Around the Pacific Ocean basin, hundreds of millions of people live in coastal communities. Some are in large cities, modern metropolises with high-rise buildings and busy ports. Others are in small towns and villages where fishing has been a way of life for generations. All of them share a common vulnerability to tsunamis. These communities are aware of the risk to varying degrees. In places like Japan, where tsunamis have struck multiple times in living memory, there's a strong culture of preparedness. Children grow up practicing tsunami evacuation drills at school. Coastal areas have seawalls, evacuation routes marked with clear signs, designated safe zones on higher ground. Warning sirens are tested regularly. Everyone knows that if you feel a strong earthquake near the coast, you don't wait for a warning, you head inland or uphill immediately. Other regions have less direct experience with tsunamis but are still at risk. Parts of the North American West Coast, Central and South America, islands across the Pacific, all these areas could be affected by a distant tsunami generated by an earthquake on the other side of the ocean. In these places, awareness can be lower. People might have heard about tsunamis but not fully appreciate the danger or know how to respond. This is where education and effective warning systems become critical. When tsunami warnings are issued, emergency managers face difficult decisions. Evacuating a coastal area is disruptive and potentially costly. Businesses shut down. Roads become congested. People leave their homes, uncertain when they'll be able to return. If the tsunami turns out to be minor or doesn't materialize, there's frustration and economic impact. But if you don't order evacuation and the tsunami is severe, the consequences can be significant. This is why accurate predictions matter so much. If warning systems can reliably distinguish between situations that require full evacuation and situations where caution is needed but evacuation isn't necessary, decision-making becomes clearer. Emergency managers can act with more confidence. The public can trust that when an evacuation is ordered, it's genuinely needed, and when it's not ordered, they're actually safe staying in place. There's also the question of what happens after a tsunami warning is lifted. The psychological impact of these events shouldn't be underestimated. Families who evacuate experience stress and uncertainty. Children are frightened. Businesses lose revenue. Even when physical damage is minimal, there's an emotional toll. Communities that experience frequent warnings, even if most turn out to be precautionary, can develop a kind of fatigue or anxiety around the issue. Better predictions help with this too. If warnings can more accurately forecast the actual severity of the tsunami, the duration of the threat, and which specific areas are at highest risk, then responses can be proportionate. High-risk zones evacuate, moderate-risk zones take precautions, low-risk zones stay alert but don't need to disrupt normal activities. This tiered approach reduces unnecessary disruption while maintaining safety. Some communities have invested heavily in physical infrastructure to reduce tsunami risk. Japan has built elaborate seawalls in certain vulnerable areas. These structures are impressive feats of engineering, designed to block or deflect tsunami waves. They're not foolproof and can create their own issues, but in some cases they provide meaningful protection. Other communities have created elevated evacuation platforms, sturdy structures built on high ground, or elevated above street level where people can take refuge if a tsunami arrives faster than expected. There are also nature-based approaches. Mangrove forests and coastal wetlands can absorb wave energy, reducing tsunami impact on areas behind them. Some communities are working to restore or protect these natural buffers as part of their tsunami preparedness strategy. It's not a complete solution, but it's a piece of a comprehensive approach that includes warning systems, evacuation planning, and physical barriers. Education is perhaps the most important element. People who understand the danger, know the signs, and have practiced what to do are more likely to survive when a real tsunami occurs. Stories from past events often highlight cases where individuals who felt an earthquake immediately moved to high ground, even without waiting for an official warning, and survived because of that instinct. That instinct comes from education and cultural awareness. In some Pacific Island nations, traditional knowledge about tsunamis has been passed down for generations. Elders tell stories of past events. Communities maintain oral histories about what the ocean does before a tsunami, how to recognize the signs, where to go for safety. This indigenous knowledge complements modern scientific understanding. Both are valuable, both save lives. There's something profound about the fact that people living on opposite sides of the ocean, who might never meet, are connected by the possibility of a tsunami. An earthquake off the coast of South America can generate waves that reach Hawaii, Japan, or the Philippines. The ocean doesn't respect national boundaries. This shared vulnerability creates a kind of global community, one that depends on international cooperation in monitoring, warning, and research. When the SWOT satellite revealed new details about tsunami behavior, the findings weren't relevant to just one country or region. They were relevant to everyone living near any ocean where tsunamis occur. The improved models being developed based on these observations will benefit coastal communities worldwide. This is science serving humanity in a very direct way. It's also worth acknowledging the resilience of coastal communities. Many areas affected by tsunamis in the past have rebuilt and recovered. People don't abandon their homes simply because of risk. They adapt, prepare, and continue their lives with an awareness of the danger, but not in constant fear. This resilience is admirable and speaks to human determination to thrive even in the face of natural hazards. At the same time, we should be realistic about limits. Not every coastal area can be made completely safe from tsunamis. Some locations are simply too exposed, too vulnerable. In these cases, land use planning becomes important, perhaps avoiding new development in the most at-risk zones, perhaps designing buildings to be more resistant to wave impact, perhaps accepting that certain areas will need to be evacuated when warnings are issued, and planning accordingly. The economic dimensions matter too. Coastal areas often depend on tourism, fishing, and shipping. These industries are vital to local livelihoods. Measures to reduce tsunami risk need to be balanced against economic realities. A massive seawall might provide protection, but could destroy the natural beauty that attracts tourists. An overly cautious approach to warnings could harm the economy. Finding the right balance requires input from the community, not just top-down decisions by authorities. What gives hope is seeing how communities come together around tsunami preparedness. Neighbours help each other. Local organisations conduct drills and education campaigns. People take responsibility for their own safety, while also looking out for others, especially the elderly, or those with mobility challenges who might need assistance evacuating. This social cohesion is a form of resilience that technology alone can't provide. The role of technology in all this is to provide information that empowers these communities. Better satellite observations lead to better models lead to better warnings, and better warnings lead to better decisions and actions by the people at risk. It's a chain that connects space-based sensors to individual families making choices about whether to leave their homes, when a tsunami warning sounds. Every link in that chain matters. The satellite needs to work correctly. The data needs to be transmitted and processed quickly. The models need to be accurate. The warnings need to be communicated clearly. Emergency managers need to make sound decisions, and individuals need to respond appropriately. When all these pieces work together, lives are saved. The story of tsunami fragmentation discovered by SWOT is ultimately a story about improving one link in that chain, the modeling and prediction link. It doesn't solve every problem, but it makes the system work better. And in the context of natural disasters, where margins can be thin and outcomes can be measured in lives lost or saved, making the system work better is profoundly important, which leads us naturally to reflect on what this all means and where we go from here as we continue learning to coexist with a dynamic planet that will never be fully predictable or controllable. So let's come back to where we started, that moment when scientists looked at their screens and saw something that made them go silent. Remember the satellite watching from orbit, the tsunami spreading across the Pacific, the patterns that didn't match expectations. Now you understand what they felt in that moment. It wasn't just surprise, it was the recognition that a hidden layer of complexity had just been revealed, and that this revelation would require rethinking some fundamental assumptions about how tsunamis behave. The journey we've taken through this story illustrates how science progresses. We don't suddenly jump from ignorance to complete understanding. We build knowledge incrementally. Each new observation adds a piece to the puzzle. Each improved tool lets us see a little more clearly. The process is gradual, sometimes frustrating, but ultimately powerful because it's grounded in evidence and reality rather than assumptions or wishful thinking. What SWOT revealed about tsunami fragmentation is now part of our understanding. It's been documented, analysed, published, and is being incorporated into the next generation of models and warning systems. This doesn't mean the work is done. Far from it. There are still questions to answer. How exactly does fragmentation affect coastal impact? Can we predict which tsunamis will fragment most severely? How do we best communicate complex wave arrival patterns to the public in ways that are understandable and actionable? Researchers are working on these questions right now. Teams are analysing more data, running more simulations, testing new approaches. The satellite continues orbiting, gathering information that will fuel discoveries we haven't even imagined yet. This is the ongoing nature of science. There's always a next question, always another layer to peel back, always more to learn. For those of you watching this who live near coastlines, especially around the Pacific, this story has practical relevance. It means the tsunami warning systems you depend on are getting better. The predictions will become more accurate. The warnings will be more reliable. This doesn't eliminate risk, but it reduces it. It gives you and your community better information to make decisions that could save lives. I'd encourage you to stay informed about tsunami preparedness in your area. Know the evacuation routes. Understand what the warning sirens mean. Talk with your family about what you'll do if a tsunami warning is issued. These conversations might feel uncomfortable, but they're important. Preparation isn't about living in fear. It's about being ready so you can respond effectively if the need arises, and then get back to living your life without constant worry. For those farther from coasts, this story still matters. It's an example of how scientific research, even esoteric-sounding studies of ocean waves, connects to real-world safety and well-being. It's a reminder that the investments we make in Earth observation satellites, in computing infrastructure, in supporting researchers, those investments pay off in ways that might not be obvious until a discovery like this happens. It's also a story about international cooperation and shared challenges. The ocean connects us all. What happens in one part of the Pacific can affect coasts thousands of miles away. The knowledge we gain benefits everyone. The technologies we develop serve humanity collectively, not just individual nations. In a world that often feels divided, this kind of scientific collaboration and shared purpose is worth celebrating. Looking ahead, we can expect continued progress in understanding and preparing for tsunamis. As ocean floor mapping improves, as satellites become more capable, as computing power increases, our ability to simulate and predict these events will keep getting better. We're moving toward a future where tsunami warnings are not just timely but genuinely precise, where communities can prepare with confidence, knowing that the information they're receiving reflects the best possible understanding of what's actually happening in the ocean. That future isn't automatic, though. It requires sustained effort and support. It requires training scientists and engineers. It requires maintaining and upgrading observation networks. It requires communication between researchers and the operational agencies that issue warnings. It requires public awareness and engagement. All of these pieces need to work together. The SWOT satellite observation that started this whole story was, in many ways, a lucky break. The satellite happened to be in the right place at the right time, but luck favors the prepared. SWOT existed because people decided to build it, fund it, launch it, and operate it. The researchers were ready to analyze the data because they had the expertise and the tools to do so. When the opportunity came, they were positioned to take advantage of it. That's not pure luck, that's preparation meeting opportunity. There's a broader lesson here about how we relate to the natural world. We live on a dynamic planet. The ground shifts, the atmosphere swirls, the ocean moves. These processes have been happening for billions of years and will continue long after we're gone. We can't control them, but we can understand them better. We can observe, learn, and adapt. We can use knowledge to reduce risk and protect ourselves. This isn't about conquering nature or bending it to our will. It's about finding our place within natural systems, understanding the rules by which they operate, and making smart decisions based on that understanding. It's about humility in the face of forces far greater than ourselves, combined with determination to use our intelligence and creativity to survive and thrive. The satellite watching the ocean is a symbol of that approach. We can't stop earthquakes, we can't prevent tsunamis from being generated, but we can watch from above, see what's happening, understand it more clearly, and use that information to give people the warning and guidance they need. That's a form of power that's achievable and meaningful. As we close, I want to return to the image that started everything. A satellite orbiting high above Earth, its instruments pointed downward at the blue expanse of the Pacific. An ocean that appears calm and uniform from that height, but is actually deeply complex, hiding a landscape beneath its surface that shapes every wave, every current, every movement of water. A tsunami spreading outward from its source, not in neat concentric circles like textbooks show, but fragmenting and scattering in response to the hidden topography below. That image changed what we know. It revealed a truth that had been there all along but invisible to us. It reminded scientists that reality is always richer than our models, and it set in motion improvements that will eventually make coastal communities safer. The satellite is still up there, still watching, still learning. The ocean continues its ancient rhythms indifferent to our observations, and we continue the work of understanding, predicting, and preparing, knowing that each small advance in knowledge, each improvement in technology, each lesson learned from past events contributes to a future where fewer people lose their lives when the ground shakes and the ocean responds. If you found this exploration valuable, hit that like button. Subscribe to the channel because there are more stories like this, discoveries that reshape our understanding of the world and have real implications for how we live. And drop a comment sharing where you're watching from, especially if you're in a coastal area with tsunami risk. Your perspective matters, your awareness matters, and the conversation we build together helps spread knowledge that could genuinely make a difference when it's needed most. Thank you for staying with me through this journey from space to sea, from mystery to understanding, from observation to action. The work continues, the learning never stops, and the ocean keeps its secrets close, revealing them only to those patient and persistent enough to look carefully and think deeply about what they see.